Guys, I would say most days I'm going to probably give you a break, just so long as you guys can, use it well. If I get feedback though from other teachers, obviously that you're disrupting classes, you can do that, right? Hey guys. Guys. Thank you. Okay. I don't mind giving a break. I think it's worthwhile just to even have a stretch. But make sure you guys don't get in trouble in the halls, okay? Not that anyone did, obviously, but just make sure I don't get feedback from other teachers that it's being a disruption. But I'm a big fan of being able to go take a stretch break. So, does that work for you guys? Okay, because we still got more. Like I said, this is one of the biggest reasons why I want to give you guys notes printed out. There's a lot of topics, and we're only like 2/3 of the way, halfway through my notes for the day. So, yay! Okay, next scientist, Niels Bohr. Not that any one scientist is more important than the other one, but if you had to ask me, if you wanted my opinion, I think that he is probably one of the most influential people that, I think he's the most important. His discoveries have been the most influential on science. And I don't think I can really describe those to you even today because it requires some physics background as well. But Niels Bohr made a really important discovery using lights and glowing tubes. And basically what he was able to conclude is that electrons are in what are called specific energy levels. I want to go back to Rutherford's idea. Rutherford's idea was that electrons went around and circled kind of like planets do. Well, what Bohr's idea was is that they can't just be anywhere where these orbits are. They have to be in very specific locations. So I can diagram this. Here's your nucleus. He concluded that electrons could be right here on this orbit here, or they could be here on this orbit, but you would never find an electron kind of like somewhere in between. Does that make sense? Before that, Rutherford's ideas was that the electrons could be kind of wherever, so long as they were going in a circle. But Rutherford's idea was that they could either be here, or here, or here, and his idea suggested that electrons, if they move from here to here, that they don't go halfway in between ever, but that instantly they jump from here to there. And that's really weird. Because if I wanted to go from here to the other side of the room, I don't just teleport over there. But this is actually what electrons do, which is crazy. Let me say that one more time. If I wanted to walk from here to the other side of the room, you'd find me partway in between. Does that make sense? Well, here's what made Bohr's idea weird, is that he thinks that electrons go around in circles. And he thinks that if they want to move, that it's possible, but that it goes instantly from here to here. You would never find the electron halfway in between. And to the best of our understanding, that's actually how the electrons work, which opens up some really cool ideas. There are some theories that believe that teleportation is actually possible, based on Niels Bohr's ideas, which is again, this is crazy new age stuff that physicists to this day are working on trying to figure out how does the electron just instantly flicker from one place to the next. Does that make any sort of sense? So anyways, this is one of the reasons why I think Niels Bohr is one of the most influential. So again, here's his idea. It's not that different from Rutherford's. He still believes in a nucleus. He still believes in electrons. But he believes that these electrons are either here, or here, or here, and never in between. It's kind of cool. So we call them energy levels. We often still draw these diagrams. Have you guys ever drawn diagrams like this before or seen them? That's something you've done? No. Final model of the atom, the quantum model. It's kind of what scientists are working on nowadays. We don't think that electrons seem to go from in circles anymore. And that idea seems to be gone. We still do fully believe and have evidence based on the whole idea that electrons all of a sudden change where they're at. But we don't seem to think they're going in circles. We actually think that they exist in, where's the word here? Clouds is kind of the modern theory. And one of the weird things about clouds that, I don't even fully understand it, just so you guys know. But they think that the electron could be found somewhere in the cloud. We just don't know where in the cloud the electron is. One of the weird things about physics is as soon as you start looking for electrons, they're already gone. I think I can explain this. See if this makes sense. Why do I see Gabe sitting right there? How does light in my eyes work? Do you guys know how this, like why I'm able to see him? Light bounces off of Gabe and to my eyes. And so therefore I can perceive that Gabe is sitting there. Does that concept make sense? Okay, here's the problem with electrons. Gabe is not an electron. Gabe is made of many electrons, obviously, right? Here's the thing. As soon as light hits an electron for us to look at it, that light will actually cause the electron to move. Let me say that again. When light hits Gabe, Gabe doesn't move. The light bounces off of Gabe and I see it. Does that make sense? Electrons are so small that as soon as I try to look for an electron, I can find it, but I find where it was, because the mere presence of the light hitting Gabe and coming to me will actually cause the electron to move, because electrons are that small. Makes sense? Even if it doesn't, that's fine, because that's some pretty high-level physics. The problem with this, then, is that we can't actually really know where electrons are. So we often draw them using these kind of like cloud kind of ideas.
Dylan Baxter, please come to the office. Dylan Baxter.
And so these cloud kind of, we call them orbitals. They're usually like ovally kind of shaped things. What they really depict is where we think the electron could be, but we don't actually know where it is, because as soon as we look for it, it's already going to be gone, because it's just that small. And it will have instantaneously zipped somewhere else. Like I said, physics is some really cool stuff if you want to learn it. What was that? That's possible too. Yeah, I mean, but there's only so many electrons, so. But I mean, it could happen. So, okay, last thing. Now I'm actually going to give you something that we can do. Most of what I just talked about there is all just history, and I really do want you to know that stuff. I'll test you on it. But now here's actually like something that I can give you a worksheet we can practice. Okay? We're going to talk a little bit about all of the things inside the atoms and how we count them up. So inside the atoms are three main components. There are protons, which I normally am going to denote with a P+. That's going to be my way of writing a proton. Proton. Electrons I usually write with an E-. That's my notation for electrons. And there was actually one more small particle that was discovered way later. I think it was in the 40s or 50s. It's known as the neutron. And usually I'll write that as an N with a little 0. The reason I write a 0 is that neutrons are neutral. They don't actually have a charge. Yeah, they're neither neutral. And so what I'd like to do is talk about, on the periodic table, how those elements relate to these three. We call them subatomic particles. Okay. So hopefully something that you guys know already is, here's a periodic table. Over here you have one in front of you. Okay. It is ranked numerically, and granted they're not always right next to each other, but it's ranked based on protons. Okay. So if you find number 1, way up there in the corner, hydrogen has 1 proton. Does that make sense? So if I were to find you silver, which is right here, number 47, how many protons does it have? 47, exactly, right? So it's ranked based on protons. That's how we've ordered it. Sometimes, though, we call the number of protons atomic number. So atomic number really is just a scientific way of saying how many protons it has. Does that work? Cool. Now, you know one of those theories that Dalton had way back in the day? Let me see if I can find it. He had this theory about how atoms are identical in mass. It was wrong. And it has to do with neutrons. If we're talking about an atom of something, let's say we're talking about a hydrogen atom. A hydrogen atom has to have 1 proton, but it can actually have different numbers of neutrons. Why can it have different numbers of neutrons? Well, because neutrons are neutral. So a hydrogen atom could have, well, it has to have 1 proton. Otherwise, it's not hydrogen. But it could have no neutrons. It could have 1 neutron. It could have 2 neutrons. And so it leads to this weird situation where each individual atom could actually have a different weight. Does that make sense? So we have a term for that. We call that its mass number. And sometimes we write it in like a symbol like this. So let me walk you through this example here. Do you guys know what C stands for? Fantastic. Carbon, yeah. Carbon is number 6. I guarantee you that because it's number 6 on the table. What does that mean? It means it has 6 protons. If it has 7 protons, it's not carbon. If it has 5 protons, it's not carbon. Does that make sense? However, each individual carbon atom might weigh a different amount depending on how many neutrons it has. This one right here weighs 12. So here's how this works. 6 of its weight, I guess, comes from protons. The other weight comes from neutrons. So if 6 is protons and an unknown amount is neutrons and it equals 12, can anyone tell me how many neutrons this thing has? Exactly. There you go. Yeah. This has 6 protons and 6 neutrons. And 6 plus 6 equals that 12 right there. Does that make sense? Okay, here comes the question then. What about electrons? Well, we've actually discovered that protons and neutrons weigh pretty much the exact same. But electrons weigh very, very little. I gave an analogy to my Chem 20 class earlier today. It would be like, let's say we were weighing 12 elephants. And then a couple of birds came and rested on those elephants' heads. Would you really notice the difference at all on a scale? No. Not really, right? That's the scope of difference that's there. Yes, electrons weigh a little bit, but really they are so small in comparison, it's completely irrelevant. So when we talk about how much something weighs in terms of mass, we're going to add up its protons, and the protons is always this lower number here based on its atomic number. We're also going to add the neutrons, and the sum of those two numbers is how heavy it is. Does that work? Let's try this one over here then. Is this still carbon?
Yeah.
Why?
It has 6 protons.
Exactly, it has 6 protons. If it had 7 protons, it would then be nitrogen. Does that make sense? However, these two things are both carbon, but they don't weigh the same. This carbon atom weighs 12, and this one weighs 14, because this guy has 6 protons and 6 neutrons. This guy has 6 protons, but he has 8 neutrons. Does that make sense why it's 8? Because 8 and 6 adds to 14. Ta-da! Any questions? You guys ever done this before?
Yeah.
Oh, fantastic. You have done this before?
No.
Oh. Oh, okay. I don't know what you guys do in grade 9, so I kind of start assuming that maybe you've learned nothing and we'll work away from there. Okay. Okay. So this is kind of new, but kind of old. Okay. Well, we're almost done. So let me walk you through my last slide. Last slide, perfect. So mass number is this top number here. Here's a hydrogen 1, here's a hydrogen 2, here's a hydrogen 3. So remember that Dalton theory. Dalton's theory was that all atoms of each type are the exact same. He's actually wrong, they're not. Here's a hydrogen that's weighing 1, here's a hydrogen weighing 2, here's one weighing 3. Why? Well, this guy has no neutrons, this guy has 1, this guy has 2. Or down here, same thing with carbon. So what I need for you guys to be able to do is solve often for how many neutrons there are. And it's really simple. If you want to figure out how many neutrons something has, you have to know its mass number. I'll have to tell you that. And you subtract its atomic number. I might not tell you its atomic number. Why might I not tell you its atomic number? Because you just look at it on the table. So if I tell you that it's scandium, you should know scandium's atomic number because it's number 21.
Akira Gooden, please come to the office. Akira Gooden, to
One
the
last
office,
thought
please.
here, then I'm going to give you guys some time to work on some stuff. On your periodic table, you know how all the things are listed? Let me just draw one out real quick. Let's do hydrogen. I can't even pick things this way. Okay, so you get like a 1, a 1.01, a +1, a -1, a 2.2, an H, and then it says hydrogen. Does that make sense, kind of what I'm drawing here off your periodic table?
Yeah.
Okay. You might recognize some of these numbers, like the H stands for hydrogen. The 2.2 we won't use for a long time. These charges. There is a number up in the top corner here that you guys maybe have used before. That is not what I just showed you. It's similar, but it's not the same thing. The reason why is that you can't have 1.01 of something in an atom. You either have 1 proton or you don't. Does that make sense? That number is actually an average of things, and we'll get to it later. If you've ever seen, you guys seen that number before? Talked about it? Okay, so if we're talking about mass number, don't use 1.01 minus 1. That doesn't fit. It's going to be a whole number. Does that work? Okay. Well, that's what I want you guys to work on now for the last 25 minutes here. I have a worksheet, and I also have some questions in your textbook I'd like you guys to give a try. Now, I'm not going to mark these for homework. I don't give homework that's due for marks. I need you guys to know something in my classes right off the bat. I need you to do this because it's going to help you learn. If you don't want to learn, then don't do it. But if you don't want to learn, you probably should go to lab-3 math class instead, okay? So if you don't finish this, I don't care. I'm not going to look over your shoulder. But I want you to want to finish it because hopefully it'll help you learn and get better. Does that make sense? If you don't have a textbook, you probably should go find one. So here's a worksheet. There's some questions. I'd like for you guys to be able to call me over and ask me questions if you don't understand, okay? That's what this time here is for. One short. Get you one second. Let's have to reprint it. Semester 1, chemistry. No, you guys are science 10. And look, it shows the map. Yeah. There's like what number it is. Sorry, Gabe. Yeah, sure. So, I